Swayam Prabha. Digital India. Educated India.
Welcome to lecture 36 of the course on econometric methods for statisticians, data scientists and data engineers. The title of this lecture is 3-stage least squares, full information maximum likelihood and K-class estimators. Now, so far we have discussed different estimation procedures like the indirect least square procedure, or two-stage least square procedure, or limited information maximum likelihood estimator for estimating the parameters of a simultaneous equations model. Now, all these estimators are called limited information estimators. Limited information in the sense that while developing these estimators, we make use of information contained in a particular equation. That is, suppose you are interested in estimating the first equation of the model, say, then while developing indirect least square procedure or two-stage least square procedure or limited information maximum likelihood estimator, we make use of information contained in the first equation only. We do not take care of the other equations of the model. Remember, in a simultaneous equations model, you have a system of equations, and then different equations may be correlated with each other. Correlated means the information about the first equation may be contained in the second equation also or the third equation also, because the disturbances of second equation or third equation may be correlated with the disturbances of the first equation. So, if you are using the limited information estimators like ILS or 2SRS, then you are not making use of that information. Then one of the option is to develop an estimator which makes use of the entire system of equations simultaneously, and then that estimator makes use of the information contained in all the equations. Say, suppose you want to estimate the parameters of a particular equation, then it makes use of the information contained in all other equations also. So, it may lead to more efficient estimators. So, in this lecture, we will discuss different full information estimators. In particular, we are going to discuss the three-stage least square estimation procedure and then full information maximum likelihood estimation. We will also discuss a class of estimators known as K-class estimators. Now, before discussing all these estimation procedures, first I am going to discuss Pagan's procedure for obtaining the limited information maximum likelihood estimator. So, for obtaining the limited information maximum likelihood estimator, let us consider the Pagan's procedure. So, suppose this is your ith equation, y I equal to z I delta I plus u I. Then the reduced form equation for capital Y I is, say, capital Y I equal to x pi I plus V I. Then we write this reduced form equation for capital Y I in vector form. So, suppose y r is vector y I, pi r is vector pi I. Similarly, small v I is vector capital V I, and capital Z I is equal to y I x I. Then we can write the reduced form in vector form as y r equal to I k I minus 1 Kronecker product x pi r plus V r. Means this is a matrix. So, to write this matrix in vector form, what we do? We just take the first column, write it, and then we take the second column. So, below the first column we write the second column, and so on. This is how we proceed. So, we get this reduced form for y I in vector form. Then we write 1 and 2 jointly. So, this is actually the basic purpose of writing this in vector form. Actually, you have to write the joint likelihood function for small y I and capital Y I. So, for that purpose we write capital Y I in vector form, then we combine it with the small y I. So, we write this form, say we combine 1 and 2, and then we write small y I y r equal to say z I 0 0 I k I minus 1 Kronecker product x. Then you have delta I pi r here and u I v r. Now, suppose the covariance between a particular component of u I and that of v r is, say, sigma I is the variance of u I, then psi transpose psi capital omega. This psi transpose is a row vector and this psi is a column vector. And then suppose inverse of this is small a C transpose C capital D. Then making use of this result, if you take partition of a matrix M as A, B, C, D, then M inverse is defined like this. So, we make use of this result, and then we can obtain A, C transpose C and capital D in terms of sigma I, psi and omega. So, we get A equal to this sigma I minus psi transpose omega inverse psi whole inverse. C is equal to this, just make use of this result, and D is equal to this. So, we get these expressions for small a, small c, small d, and of course, you can get C transpose also from here. So, you get the elements of inverse of this matrix, and then from 3 we can obtain the estimators, say d I L I M L pi hat L I M L as, say, notice that if you look at this equation 3, it is just like the multiple linear regression model y equal to x beta plus u, and u has, say, normal 0, and you take the variance matrix as, say, omega. Then the maximum likelihood estimator is beta hat equal to x transpose omega inverse x inverse x transpose omega inverse y. So, this is the GLS estimator, and this GLS estimator is MLE also. So, we obtain this estimator d I L I M L pi hat LIML equal to ZI transpose, then in between you have the inverse elements A canonical product IN ZI transpose C transpose canonical product X, then C canonical product X transpose ZI D canonical product X transpose X whole inverse. Then you have ZI transpose A canonical product IN ZI transpose C transpose canonical product X, then C canonical product X transpose D canonical product X transpose YI YR. And again you can obtain inverse of this matrix, this partition matrix. Just make use of this result again. And mainly actually you are interested in the expression for DILIML. So, you get DILIML equal to, so mainly you want the element present here in the inverse of this matrix and the element present here in the inverse of this matrix. So, you get this expression for DILIML sigma I q ZI transpose P yi plus A q ZI transpose P bar yi, where P bar is equal to IN minus X transpose X inverse X transpose plus Q ZI transpose C transpose canonical product P bar YR. So, you get this expression for the limited information maximum likelihood estimator. Simply you have to obtain the inverse of this matrix by using the result about the inverse of partition matrices, which I mentioned earlier, and then you multiply these two, and again you multiply by yi yr, and then find out the elements corresponding to DILIML. You get this expression. Now, suppose you write ZI hat equal to yi hat xi and say wi hat equal to zi minus zi hat. Then q inverse is equal to sigma I inverse zi hat transpose zi hat plus A wi hat transpose wi hat. Just take this q and then you take inverse of this. So, you can easily verify this expression for the inverse of q, and then we make use of this expression for q inverse and we obtain DILIML equal to, the first expression reduces to the two stage least square estimator. Here you have zi hat transpose zi hat, and then you write the expression for q equal to this inverse. From there you substitute it here, sigma I will cancel out, and finally you obtain this expression, and along with this expression for 2 SLS you also obtain these expressions. Now, this gives you a relationship between 2 SLS and LIML estimators. So, using this approach you can find the expression for limited information maximum likelihood estimator, and you also get the relationship between limited information maximum likelihood estimator and 2 SLS estimator from here. Now, we consider full information methods of estimation. So, while defining indirect least square, two-stage least square or limited information maximum likelihood estimators, we only consider a particular structural equation, or suppose you want to estimate the parameters of a particular structural equation, then we only consider the information contained in that particular equation, and all other structural equations in the model have not been taken into account. So, in this sense, these estimators are called limited information estimators. Now, in full information estimators, other equations and the fact that structural disturbances of various equations may be correlated is utilized in the estimation process. So, it is possible that the disturbances of various equations are correlated with each other. So, the other equations also have information about that particular equation which we want to estimate. So, in full information estimation procedures, we also make use of that information. So, it is just like the seemingly unrelated regression equations model. In seemingly unrelated regression equations model, you have two options. Say, suppose you have two equations, y 1 equal to x 1 beta 1 plus u 1 and y 2 equal to x 2 beta 2 plus u 2. Then you apply OLS to first equation, estimate beta 1. You apply OLS to the second equation, estimate beta 2. So, you apply estimation procedures to the two equations separately. Now, in seemingly unrelated regression equations, often u 1 and u 2 are correlated. So, it means the second equation has some information about the first equation also, or the first equation has information about the second equation also. So, you may combine the two equations and then apply some estimation procedure like GLS to the combined model, then it may lead to more efficient estimator. Similarly, here also for simultaneous equations model, you may combine all the structural equations and then you try to develop a combined estimator, then it may lead to more efficient estimators, because then you are making use of the correlation between different structural equations. So, in principle, information on complete system would yield estimators with improved efficiency properties. Now, suppose you consider this ith equation y I equal to capital Y I beta I plus x I gamma I plus u I equal to 1 to m. Then we write z I equal to capital Y I x I delta I equal to beta I gamma I. And then you can write this equation 1 as small y I equal to z I delta I plus u I equal to 1 to m. Now, the two-stage least square estimator of delta I is, say, d I 2 SLS, we denote it by d I 2 SLS equal to z I transpose x, x transpose x inverse, x transpose z I whole inverse, z I transpose x, x transpose x inverse, x transpose y I. So, this is your 2 SLS estimator for delta I. For obtaining this estimator, just concentrate on this ith equation. Now, suppose you take x transpose y I, means you multiply this equation by x transpose, then x transpose y I is equal to x transpose z I delta I plus x transpose u I for all I equal to 1 to m. Now, we stack all the capital M equations. Remember how we obtain the 2 SLS estimator. We consider this equation, then we apply GLS for estimating delta I to this equation, and when we apply GLS to this equation, we get this estimator. So, again we consider this equation for all I equal to 1 to m, and then we combine all these equations. So, stacking all the m equations, we obtain x transpose y 1, x transpose y 2, so on x transpose y m equal to, then you write it as say x transpose z 1 0, so on 0, 0 x transpose z 2, so on 0, and so on 0 0, so on x transpose z m into delta 1 delta 2 delta m plus x transpose u 1 x transpose u 2, so on x transpose u m. So, in fact, we are using the same approach which we used in seemingly unrelated regression model. And then we write the left hand side as I m canonical product x transpose y. If you take I m canonical product x transpose, then what you get? This is equal to x transpose, you get x transpose, and here you get 0. And if you multiply it by y, so you get x transpose y 1, you multiply it by y, so you get x transpose y 1, x transpose y 2, so on x transpose y m. Equal to I m canonical product x transpose, then you have z delta plus I m canonical product x transpose u, where this z is n m cross summation I equal to 1 to capital M m I minus 1 plus k I matrix. In fact, corresponding to the ith equation, how many columns are there in Z? M I minus 1 plus k I. The ith equation has m I minus 1 endogenous variables and then small k I predetermined variables. So, total number of columns in Z is summation I equal to 1 to m I minus 1 plus k I, and total number of rows is say corresponding to each Z you have n rows, then you have capital M into small n rows in capital Z. Similarly, delta is of order summation m I minus 1 plus k I cross 1. Now, expectation of u I transpose is equal to sigma I n, and expectation of u j transpose is equal to sigma I j I n. So, even for I not equal to j, u I and u j are correlated with each other. Then capital sigma is m cross m matrix with I jth element sigma I j. Then the covariance matrix of x transpose u 1, x transpose u 2, so on x transpose u m is, so you simply take expectation of x transpose u 1, x transpose u m, and then you take transpose of this. So, u 1 transpose x, u m transpose x. So, what you get here? Here you get sigma 1 1, because expectation of u 1 transpose is sigma 1 1 x transpose x, then you have sigma 1 2 x transpose x, and so on. So, finally, you obtain this matrix. So, this is the variance covariance matrix of x transpose u 1, x transpose u 2, so on x transpose u m. And then you can write this variance covariance matrix as capital sigma canonical product x transpose x. So, this is the expression for the variance covariance matrix of this. Now, we apply generalized least square estimation procedure to this equation 5. This is your equation 5, and then we obtain the 3 SLS estimator. So, the procedure is just very similar to the procedure of obtaining GLS estimator in seemingly unrelated regression equations model. There also we combine all the equations and then we apply the GLS procedure. So, we obtain the expression for 3 SLS estimator as delta curl 3 SLS equal to, you have transpose of this matrix means Z transpose I m canonical product x transpose whole transpose, in between you have inverse of sigma canonical product x transpose. So, you get sigma inverse canonical product x transpose x inverse, then I m canonical product x transpose z whole inverse multiplied by z transpose I m canonical product x transpose transpose, then you have sigma inverse canonical product x transpose x inverse, then I m canonical product x transpose y. So, you get this expression, and then we simplify it. Actually, transpose of this is I m canonical product x, and then we multiply it by this matrix, and then you have this matrix also. So, if we multiply all these 3 matrices, then we get Z transpose. We make use of this results A canonical product B into C canonical product D equal to A C canonical product B D. So, you obtain sigma inverse canonical product x transpose x inverse x transpose z whole inverse. Then you have z transpose here, we multiply these 3. So, we get sigma inverse canonical product x transpose x inverse x transpose into y. So, this is the expression for 3 SLS estimator, and for estimating sigma I j we can use this consistent estimator. So, S I j equal to y I minus z I d I 2 SLS transpose y j minus z j d j 2 SLS divided by n, because this expression for 3 SLS estimator involves sigma, and the I jth element of sigma is sigma I j, which is usually unknown. So, what we do? We obtain a consistent estimator of sigma I j based on the 2 SLS estimator. So, we estimate sigma I j using S I j, and then to obtain a feasible 3 SLS estimator, we replace the elements of capital sigma, that is sigma I j by S I j. And in Sij, in place of n, we may divide by say n minus mi minus ki plus 1 to the power half, n minus mj minus kj plus 1 to the power half. It is just like the seemingly unrelated regression model, but in fact, for large n it does not make much difference. So, if we replace sigma ij by Sij, we get the feasible 3 SLS estimator as say delta curl 3 SLS equal to Z transpose S inverse canonical product x transpose x inverse x transpose Z whole inverse Z transpose S inverse canonical product x transpose x inverse x transpose y, where capital S has the ijth element Sij. So, in sigma you have simply replaced sigma ij by Sij to obtain capital S. Now, we prove this result in 3-stage least square estimator. If sigma ij equal to 0 for all I not equal to j, then the estimator reduces to the 2 SLS estimator, and it makes sense also. So, if sigma ij is equal to 0 for all I not equal to j, it means different structural equations are uncorrelated with each other. So, the information about the ith equation is not available in any other equation. So, there is no point in going for the 3 SLS estimator in this case. To prove this result, in sigma inverse, say you write sigma inverse equal to small sigma superscript ij. This is the ijth element of capital sigma inverse. Then, if sigma ij is equal to 0 for all I not equal to j, then obviously this capital sigma is a diagonal matrix with elements sigma 1 1, sigma 2 2, sigma m m. And if capital sigma is a diagonal matrix, then its inverse is also a diagonal matrix with elements 1 upon sigma 1 1, 1 upon sigma 2 2, so on 1 upon sigma m m. Further, sigma superscript I j is equal to 0 for all I not equal to j. Z transpose sigma inverse canonical product x transpose x inverse x transpose z is equal to this matrix. Means in the diagonal you obtain sigma 1 1 z 1 transpose x transpose x inverse x transpose z 1 and so on sigma m m z m transpose x transpose x inverse x transpose z m, and at all other places you get these 0 matrices. So, the expression for this is this one. Then we obtain the expression for Z transpose sigma inverse canonical product x transpose x inverse x transpose y. If we solve it, then we get the expression summation j equal to 1 to m sigma 1 j z 1 transpose x transpose x inverse x transpose y j and so on, summation j equal to 1 to m sigma m j z m transpose x transpose x inverse x transpose y j. Now, notice that sigma I j is equal to 0 for all I not equal to j. So, say if we consider this expression, all the terms are equal to 0 except the term corresponding to j equal to 1. So, we obtain sigma 1 1 z 1 transpose x transpose x inverse x transpose y 1 and so on. In this last expression, all the terms are equal to 0 except the term corresponding to j equal to capital M, which is sigma m m Zm transpose x, x transpose x inverse, x transpose ym. Then to obtain the expression for 3-stage least square estimator, we combine the inverse of this expression, you require inverse of this expression and this expression. So, the expression for 3-stage least square estimator is now, you take sigma 1 z 1 transpose x, x transpose x inverse, x transpose z 1, so on. Here you have 0 and then sigma z m transpose x, x transpose x inverse, x transpose z m, and then you take inverse of this matrix into, you have this expression here, sigma 1 z 1 transpose x, x transpose x inverse, x transpose y 1 and so on, sigma z m transpose x, x transpose x inverse, x transpose y m. Now, if you take inverse of this matrix, then the inverse of this matrix is, say you get inverse of this and so on, inverse of this here, and then you multiply it by this one. So, what you get? Inverse of this means 1 upon sigma 1 1, and you have sigma 1 1 here. So, sigma 1 1 will cancel out. Then you have z 1 transpose x, x transpose x inverse. So, you get z 1 transpose x, x transpose x inverse, x transpose z 1 whole inverse, and from here you obtain z 1 transpose x, x transpose x inverse, x transpose y 1. Now, this is the 2-stage least square estimator of delta 1. So, you get delta head 1 2 SLS. Similarly, you get the other elements also, say at the second place you get delta head 2 2 SLS and so on, delta head m 2 SLS. So, ultimately your 3-stage least square estimator reduces to the 2-stage least square estimator if sigma I j is equal to 0 for all I not equal to j. And since various structural equations are uncorrelated with each other, so you can say that the information about any particular structural equation is not contained in other equations. So, there is no point in going for the 3-stage least square procedure. You simply stick to the 2 SLS procedure. So, usually the 3 SLS procedure is asymptotically more efficient than the 2 SLS estimator, but of course, it is more complicated also. And then 3 SLS estimator requires a much detailed specification for the equation system than 2 SLS estimator does. Means suppose you have to estimate the parameters of a particular equation using the 2 SLS procedure, then what you require? You just require the specification for that particular equation, the list of all endogenous variables and predetermined variables included in that particular equation, and the list of all predetermined variables included in all the equations. But if you want to apply the 3-stage least square procedure, you require a specification for all the equations. So, 3 SLS requires a much detailed specification for the equations system. Then 3SRS requires all variables in the equations to be estimated and all predetermined variables of the system. Whereas, for 2SRS you only require predetermined variables, all predetermined variables of the system, and only those variables of the system which are included in that particular equation. Now, if some equation of the system is misspecified, this affects the 2SRS estimator of that equation, but not those of other equations. So, this is the advantage which you get in 2SRS. If a particular equation is misspecified, it only affects the estimators for that particular equation. It does not affect the estimators for other equations. Whereas, for 3SRS estimators, what you do, you combine all the equations and then you obtain 3SRS estimator. So, naturally, any such misspecification is going to affect all the estimators or estimators of all the equations of the system. So, this is a big disadvantage with 3SRS estimator, or you can say this is the cost which you have to pay for obtaining more efficient estimator. Then, for applying 3SRS, all equations of the system must be identified. If you are applying 2SRS estimator, you only require the condition that that particular equation is identified, either just identified or over identified. So, even if some other equation of the system is unidentified, you can apply 2SRS procedure. But if you want to apply the 3SRS procedure, then all the equations must be identified. Now, we consider the full information maximum likelihood estimator. Say we consider the model y equal to z delta plus u follows normal 0 sigma canonical product I n. So, we combine all the equations in the system here, and then assuming the normality of disturbances, you can write the PDF of u as 2 pi to the power minus m n by 2 sigma canonical product I n to the power minus half exponential minus half u transpose sigma canonical product I n inverse u. Then your objective is to estimate delta equal to delta 1 transpose 1 delta m transpose whole transpose. So, you write the likelihood function as say L delta sigma given y z equal to, you have 2 pi to the power minus m n by 2 determinant sigma canonical product I n to the power minus half, then you get determinant of b to the power n, and then exponential minus half y minus z delta transpose sigma inverse canonical product I n y minus z delta. So, you get this expression for the likelihood function, and then we take the log likelihood function, and in the log likelihood function we ignore the constant term, means we ignore the term involving 2 pi or other constants. So, you get log likelihood function as minus n by 2 log determinant value of sigma plus n times log determinant value of b minus half y minus z delta transpose sigma inverse canonical product I n y minus z delta. And then to obtain the maximum likelihood estimators, we maximize the log likelihood subject to the restrictions on the parameters capital gamma, capital B and capital sigma, means you have some restrictions on all these parameters and you require all those restrictions for the identifiability of different equations. So, we maximize this log likelihood function subject to those restrictions, and then you get the full information maximum likelihood estimators of parameters. Of course, I am not going into the much details of the derivations, but the basic method for the obtaining full information maximum likelihood estimator of parameters is to write this log likelihood function for the combined model. We combined the model for all the m equations, and then we write this log likelihood function, and then we maximize this log likelihood function subject to the restrictions on all these parameters. So, this is the basic procedure. Now, we consider a family of k class estimators. The family of k class estimators is defined as, say, delta I hat k equal to y I transpose y I minus k v I hat transpose v I hat. So, we introduce a scalar k here, and then you have y I transpose x I transpose y I, x I transpose x I here. You take inverse of this, then y I transpose minus k v I hat transpose x I transpose you have here y I. In fact, here v I hat is equal to y I minus y I hat. Y I hat is the predicted value of y I. Then for k equal to 0, this term disappears from here, this term disappears from here. So, delta I hat k reduces to the ordinary least squares estimator, means you have the equation small y I equal to y I x I, then you have delta plus u I. You simply apply the OLS procedure for estimating delta. So, for k equal to 0, you get the OLS estimator. For k equal to 1, if you take k equal to 1, then you get the 2 SLS estimator. You can easily verify it. And if value of k is the smallest root of the equation mod w I minus lambda w equal to 0, then delta I hat k reduces to the limited information maximum likelihood estimator. So, we obtain the roots of this equation, say w I and w are as defined earlier, and then we take the smallest root of this equation, and then we substitute that smallest root here. It leads to the limited information maximum likelihood estimator. Again, I am not going into the details of derivation here. Then we consider a family of instrumental variable estimators. Again, we consider the system of structural equations. We consider all the structural equations together. Then the instrumental variable estimator is defined as, say, delta hat I v equal to, we take this matrix of instrumental variables w. So, you get the estimated w transpose z whole inverse w transpose y. So, w is the matrix of instruments of the same dimension and rank as z. So, the dimension of w is the same as the dimension of z. Then we also assume that the probability limit of 1 upon n w transpose u is equal to 0. The probability limit of 1 upon n w transpose z is equal to sigma w z. And this sigma w z is a non-singular matrix. Of course, it is finite also. then the probability limit of delta hat I v is equal to the probability limit of 1 upon n w transpose z whole inverse. Then you have probability limit of 1 upon n w transpose. Then we write y equal to z delta plus u. So, you get probability limit of 1 upon n w transpose z into delta plus probability limit of 1 upon n w transpose u. So, ultimately you obtain delta plus the probability limit of 1 upon n w transpose u, which is equal to 0. Further, if you take the probability limit of delta hat I v minus delta hat I v minus delta transpose, then you obtain 1 upon n. The first term has probability limit sigma w z inverse, then the probability limit of 1 upon n w transpose, then in between you have the variance covariance matrix of u, which is sigma canonical product I n. In fact, if you take delta hat I v minus delta, then you get w transpose z inverse w transpose u. So, you make use of this expression, and then you have sigma z w whole inverse. So, ultimately this probability limit is also a finite matrix. Delta hat I v is a consistent estimator, because you get 1 n here. So, as n tends to infinity, the asymptotic variance covariance matrix tends to 0. In fact, the asymptotic distribution of under root delta hat I v minus delta is normal with mean vector 0 and covariance matrix sigma w z inverse probability limit of 1 upon n w transpose sigma canonical product I n w sigma z w inverse. Again, I am not giving you the derivation of this result. Then for OLS estimator, you have OLS estimator z transpose z inverse z transpose y. The matrix of instrumental variables is w equal to z. So, if you set w equal to z, then you get this OLS estimator. But the problem with OLS estimator is the probability limit of 1 upon n z transpose u is not equal to 0. So, it does not satisfy the condition that probability limit of 1 upon n w transpose u is equal to 0. So, the OLS estimator is inconsistent. Now, if you consider the two-stage least square estimator, this is the expression for two-stage least square estimator. So, in two-stage least square estimator, actually w is equal to, or w transpose is equal to this matrix. So, w transpose is z transpose I canonical product x, x transpose x inverse x transpose. So, if you set w transpose equal to this, then you get the two-stage least square estimator. And in this case, the probability limit of 1 upon n w transpose u is equal to 0. So, 2 SLS is a consistent estimator. Further, if you take the 3 SLS estimator, then this is the expression for 3 SLS estimator. So, here if you set w transpose equal to z transpose sigma hat inverse canonical product p, then you get the 3 SLS estimator. And in fact, again I am not giving you the detailed derivation, but probability limit of 1 upon n w transpose u is 0 here also. So, 3 SLS estimator is also consistent. So, in this lecture we have discussed different full information estimators like 3-stage least square estimator, or full information maximum likelihood estimator. The advantage with these full information estimators is that usually these estimators are more efficient than the limited information estimators like 2SLS estimator or limited information maximum likelihood estimator. But the disadvantage is that these estimators require complete specification of all the equations in the system, and if any particular equation is misspecified, it is going to affect the estimators of all the parameters of the system. So, suppose first equation is misspecified, then if we use full information estimators, it is going to affect the estimators of second equation also, third equation also, and so on. Whereas, for limited information estimators like 2SLS, if any particular equation is misspecified, then it affects only the estimators of that particular equation. So, this is the disadvantage of using full information estimator. So, I am going to stop here. Thank you.
Hello, I am Shikha Dikshit. I teach psychology and I am with the Department of Humanities and Social Sciences at IIT Kanpur. Today I am going to talk about what is health psychology. In the recent past, health psychology has emerged as one of the important areas in psychology. It is a field of study where psychological theories and concepts are applied to understand issues regarding health and illness. The two major themes which health psychologists are interested in studying are the themes of illness experience and behaviors associated with that experience. Contemporary health psychology adopts various and diverse kind of perspectives to understand health and illness issues. These perspectives include the behavioral perspective, the societal perspective and the cultural perspective. If we try to enumerate the kind of topics that health psychologists study, the range is very wide. To name a few of the topics, health psychologists study cognitions related to illness, that is health and illness related cognitions, social cognitive aspects of health and illness, cognitive adaptation, chronic illness and adaptation to chronic illness, disability, stress and management of stress. Health psychologists also study topics such as health related quality of life, social support and various kinds of coping mechanisms that people adopt to deal with illness experience. In addition to this kind of experience, health psychologists also study healthcare systems, health promotion and treatment related aspects including doctor-patient relationships. So, as we see, the range of topics is very large. Health psychologists also use qualitative methods and they study topics such as narratives of illness experience as well as social representations of health and illness. So, we see that the range of these topics is very large. However, this is not an exhaustive list. More recently, some health psychologists have adopted a critical health psychology approach. These health psychologists are, they offer a critique of mainly of the biomedical and behavioral perspective of health and illness, as well as the methods and approach which is used to understand health and illness. So, critical health psychologists focus on the social, cultural and political aspects of health issues. If we look at the methodological aspects, overall health psychologists adopt quantitative methodology, they also use qualitative methodology, and many health psychologists use the mixed method approach.